Hello everyone. So in the previous class we discussed about characteristic of a field, and we knew that characteristic of a field is the least positive integer, say n, satisfying the condition n into the multiplicative identity 1 should give you 0. Now we'll continue the discussion. Let's see a proposition. Suppose if characteristic of a field is a prime number p, then we have to prove that a plus b whole to the power of p is a to the power of p plus b to the power of p, as well as a minus b whole to the power of p is a to the power of p minus b to the power of p for all a and b coming from f. And the second thing is the map phi from field f to f defined by this. We have to show that this mapping is an injective homomorphism, and further, if f is a finite field, then we have to show that phi is an automorphism, and this automorphism is called as Frobenius map. Now let's say the first one. Let us consider a plus b whole to the power of p for any a and b coming from field f, and let's apply the binomial theorem. What your binomial theorem says? It is PC0, the first term a to the power of p into b to the power of 0. b to the power of 0 is 1 and PC0 is 1. So simply a to the power of p will come plus PC1 a to the power of p minus 1 into b plus PC2 a to the power of p minus 2 into b square, etc. PCP minus 1 a into b to the power of p minus 1 plus PCP, which is 1 into a to the power of 0. a to the power of 0 is also 1. So the simply remaining is b to the power of p. And you should note that what is your PC1? You should note that it is simply p, and PC2 p into p minus 1 by 2, etc. So in all this p is present. Therefore all these are integers which are divisible by p. And when the characteristic of a field is p, we knew that p can be written as p into 1. And when the characteristic of a field is p, p into 1 is simply 0. So this becomes 0. 0 into anything is 0. Similarly, PC2, p into p minus 1 by 2, where p can be written as p into 1. And p into 1 is 0 according to this. Therefore, 0 into anything is 0. So in all these, p will be present, which can be written as p into 1, and p into 1 is 0 by this, because characteristic of a field is p. Therefore all these become 0. So simply remaining is a to the power of p plus b to the power of p. So we have proved a plus b whole to the power of p is a to the power of p plus b to the power of p for all a and b coming from field f. Now let's prove the other one, that is a minus b whole to the power of p is a to the power of p minus b to the power of p for all a and b coming from field f. Here p may be a even prime or odd prime. We knew that there is only one even prime. That is, if p equal to 2, then 1 and minus 1, their values are one and the same, because if you send this one to this side, that becomes plus 1, and that is 2. 2 into 1 is equal to 0 under modulo 2. So a minus b whole to the power of p, which can be written as, because your minus 1 is same as 1, this is a plus b whole to the power of p, and we have proved that a plus b whole to the power of p is a to the power of p plus b to the power of p. But plus 1 is same as minus 1, therefore this becomes a to the power of p minus b to the power of p. So when p is an even prime, the result is true. That is, a minus b whole to the power of p is a to the power of p minus b to the power of p. Now let's go for odd prime. Suppose if p is an odd prime, then a minus b whole to the power of p, which can be written as a plus minus b whole to the power of p, by the result 1, this one, we can write this one as a to the power of p plus minus b whole to the power of p, which can be factored as a to the power of p plus minus 1 to the power of p into b to the power of p. But because p is an odd prime, obviously this will become minus 1, So minus 1 into this, which gives you the answer. Therefore, we have proved the result, that is a minus b whole to the power of p is a to the power of b minus b to the power of b for all prime. So this completes the proof of first part. Now let's go for second one. So they are given a map phi from f to f defined by phi of a equal to a to the power of p for all a belongs to f. We have to show that this mapping is injective homomorphism. Let's prove it is homomorphism first. So for all a and b coming from field f, your image of a plus b under the mapping phi is given by a plus b whole to the power of p by this definition. So a plus b whole to the power of p. But just now we have proved a plus b whole to the power of p can be written as a to the power of p plus b to the power of p. But what is your a to the power of p? It is phi of a plus, what is this one? Phi of b. So first condition of homomorphism is satisfied. Now let's go for second one. Image of AB under the mapping phi is, by this it is AB whole to the power of p. But this can be written as a to the power of p into b to the power of p. But a to the power of p is phi of a and b to the power of p is phi of b. Therefore both the conditions of homomorphism are satisfied. Therefore phi is a homomorphism of f. Now let's verify 1 1. This mapping is 1 1 or not. So assume that any two images are equal. Then we have to show that those two elements are equal to say that this mapping is 1 1. Now what is your phi of a? It is a to the power of p. And what is your phi of b? It is b to the power of p. So this can be rewritten as 0 equal to a to the power of p minus b to the power of p. But by the first proof, we have proved a minus b whole to the power of p is a to the power of p minus b to the power of b. By that, we can write like this. And this can be factored into a minus b into a minus b whole to the power of p minus 1. And you know that product of any two numbers equal to 0 in an integral domain, provided one of them is 0. So by that, since there are only p times a minus b is there, your a minus b must be equal to 0. Because your f is a field and every field is an integral domain. Therefore, this property is true. If a minus b equal to 0, that implies that a equal to b. So we have proved if phi of a equal to phi of b, then a equal to b. Therefore, this mapping is an injective homomorphism. Now further, suppose f is a finite field, then because this mapping is 1 to 1 and these two are finite and they are one and the same. Therefore, every element of codomain is having image from domain. Hence, every element of codomain which is having an image from domain, that implies that that mapping is onto. Or in other words, your range is nothing but codomain. Therefore, this mapping is surjective. Hence, this mapping is an automorphism which is called as Frobenius map. And this completes the proof. Now let's move on to a remark. What is that? Suppose f is a finite field. Then, as we have defined in this case, if E is a mapping from field F to field F, image of A is pth power of A. So there is an element in the field F which is having a pth power. And remember that is also in the same field F. So in general we can say that image of field F is F itself. That is F and F to the power of P are one and the same. How about any element in F to the power of P? They are collection of all elements of the form A to the power of P, where A is an element in F. That is, every element of F has pth root. Or equivalently, you can say that every element of F is a pth power of some element. For example, suppose if you consider Z2 is your field, then take Z2 to the power of 2, that becomes your field F, which consists of field elements 4, because in Z2 there are 4 elements are there. So I'm considering 4 elements. Say it consists of 4 elements: 0, 1 bar, x bar, 1 bar plus x bar. And remember, we have constructed the field F using Z2 and with the property that 1 plus x bar square equal to 0. Now, you should note that 0 to the power of 2 is 0 and 1 bar to the power of 2 is also 1. What about x bar square? Your x bar square, by this property, it is minus 1 bar minus x. But under modulo 2, your minus 1 is simply plus 1 and minus 1 is plus 1. So this is 1 plus x, which is again present in F. And what about 1 bar plus x bar whole square? If you expand it, you'll get this. But under modulo 2, this is 0. So simply you'll get 1 plus x bar square. But by this property, it is simply minus x. But under modulo 2, minus x is simply x, which is again a field element in F. So in this case, your F square is same as F, where F is Z2. So this is one such example. Now let's move on to next, field extensions. Suppose K is a field containing the field F, or in other words, F is a subfield of K. Then K is the extension field of F. And it is denoted by K over F, or by this diagram. Usually we write this instead of this. And the following tree diagram shows the extension fields of K, Q, where Q is the set of rational numbers. We knew that Q is subset of this. This is also a field, and this is also a field, but this is a field of this. Therefore, this is an extension field. And in fact, this is present in R. Therefore, this is again subfield of R. Therefore, R is the extension field of this. Hence, R is an extension field of Q. And R is again subfield of C. Therefore, C is the extension field of R. Hence, Q is a field of this is a field of this is a field of this. Therefore, Q is a field of C. Therefore, extension field of Q is C also. So, this is subset of this, which is a field. Therefore, this is extension field of Q. This is again subset of R. Therefore, R is the extension field of this. So, you can. And remember, this is subset of Q of I. And Q of I is subset of C. This is not subset of R, remember. Therefore, this is not extension field of Q of I, R. But Q of I is subset of this. Therefore, C is the extension field of Q of I. So like this, you can construct many extension fields. And in fact, you should see that your extension field, in fact, becomes a vector space over the field F with respect to the usual addition in K. Because K is a field, it is a abelian group under addition. And the scalar multiplication, that is, say, some A into X, for all A belongs to F and X belongs to K, is valid. Because you know, your field F is subset of K. So any element which belongs to F is also present in K. Therefore, if A is present in F, then that is also present in K, and X belongs to K is also an element of K. Therefore, their product is obviously belongs to K because of closure law under multiplication. Therefore, all the properties of vector space are satisfied for K over the field F. That means whatever the property of vector space that we have discussed can be applied for extension fields. because K is a vector space over F. Hence, the first thing which comes is dimension of a vector space. We know that dimension of a vector space is nothing but the number of elements present in the basis of that vector space. That is called as dimension of the vector space. Number of elements present in the basis of a vector space or the field F is called as dimension. So, if dimension of K or the field F is denoted by this symbol, which is one and the same as this, but this is nothing but degree of the field extension K over F. So dimension of the vector space of K over the field F is same as degree of the field extension K over F. So dimension of K is nothing but degree of the field extension K over F. And at given exercise, you show that K is a vector space over F with respect to the above binary operations. And we knew one field extension is finite. If the degree of the field extension is finite, then it is finite. Otherwise, it is infinite. For example, let us see F over F. That is, we knew that the field over itself is a vector space. And how many elements are needed to generate this field? Only one, because see, when we say a set is a basis, first thing, if it is linearly independent, and the second condition, it spans the vector space set. What is meant by span? Every element of this vector space set can be written as linear combination of these basis vector. In fact, suppose if you say A is an element in this field, then A is equal to A into 1, which is a linear combination. Therefore, 1 is the basis of this extension. And therefore this is finite. Dimension of F over F is 1. And in this case, the set of all complex numbers, we knew that every element of this is of the form A plus IB, where A and B comes from R. Therefore, every complex number can be written as A into 1 plus B into I. That is linear combination of 1 and I, where A and B are coming from field F. Like usually we write, suppose alpha is a vector in this, then alpha is equal to some C1 into alpha 1 plus C2 into alpha 2, etc. Cn into alpha n, like that. So here we have written every element of this vector space as linear combination of 1 and I. That is some scalar from R into 1 plus some scalar into I. So every vector of C is linear combination of this. Hence, the basis of C consists of 2 elements. Therefore, degree of this field extension, that is C over R, is 2. Hence, it is finite. Now, in the case of this set of all Q of cube root of 2, that is elements of the form A plus B into cube root of 2. Here, every element of this is generated by 3 vectors. This forms the basis. In fact, you'll come to know this one in the later class, that how easily you can obtain the basis elements. Therefore, the dimension of this extension or degree of this extension is 3. And see these two. The extension field, because we know that Q is subset of R, and R forms a vector space over the Q. And how many elements generates R? In fact, there are infinitely many elements which generates R. And how about this? You should note that it needs infinitely many elements in the basis to generate, say, 1, x, x square, x cube, etc. In general, R of x by R, where R of x is the quotient polynomial, that is field of quotients of R of x, that is polynomials of the form f of x by g of x. This can be generated by 1, x, x square, etc. In fact, this is linearly independent, hence the basis of R of x cannot have finitely many elements. Therefore, R of x by R is an infinite extension in general. Note, if there are n elements in the basis, then say for example alpha 1, alpha 2, etc. up to alpha n, then we knew that the degree of the field extension is n, and any vector of alpha can be uniquely written as linear combination of these n vectors, say C1 alpha 1 plus C2 alpha 2, etc. up to Cn alpha n, where each of these Ci comes from field F. And in fact, we can generalize this one like this. So this gives a bijection. We have proved this result in the vector spaces class. This gives a bijection from K to Fn, that is F Cartesian product of F vector field F n times, which is defined by alpha to n tuples, C1, C2, etc. up to Cn. Hence, if F is countable, then we knew that the set of all n tuples are countables. Therefore, K is also countable. And in particular, any finite extension of a rational set is countable because Q is countable. And the field extensions of degree 2, 3, 4, 5 are called quadratic, cubic, quadic and quintic extensions. So this is quadratic extension. This is cubic extension. These are examples of quadratic and cubic extensions. Thank you.